In a delta-delta transformer, a jumper between the bonding bushing and the case is not typically necessary for electrical functionality. The bonding bushing is used to connect the transformer case to the facility's grounding system, while the case provides a path for fault currents to return to the source. In a delta-delta configuration, the current flowing through the case is minimal, so a jumper is not required to ensure proper grounding. The presence of 21 amps on a 1/0 copper jumper connecting the bonding bushing to the case is unusual. Normally, the current flowing through the case, and therefore the jumper, would be negligible, typically less than a few milliamps. Let us explore the possible causes for high current on the jumper. One possible cause is a ground fault. A fault in the transformer windings or connections could be causing current to leak into the case. Another possible cause can be from an improper grounding. If the facility's grounding system is not properly connected or sized, it could result in higher than expected current flowing through the case and jumper. Induced current is another possibility. Electromagnetic fields from nearby equipment or wiring could induce current into the transformer case and jumper. This is more likely to occur if the jumper is in close proximity to high current conductors. Given these possibilities, it is recommended to investigate the cause of the high current on the jumper. This investigation can involve, firstly, inspecting the transformer for any physical damage or loose connections, secondly, testing the grounding system to ensure proper connectivity and size, and thirdly, checking for any nearby sources of electromagnetic interference. If the cause cannot be readily identified, it may be necessary to contact the equipment manufacturer or a qualified electrician for further troubleshooting. Let's delve deeper into each of these areas, starting with the transformer inspection. When inspecting the transformer, pay close attention to the bushings, looking for any signs of cracking, arcing, or contamination. Check all connections to ensure they are tight and free of corrosion. Use a thermal camera to scan the transformer for hot spots, which could indicate a winding fault or insulation breakdown. Also, smell for any unusual odors, such as burning insulation, which could signal an internal problem. If you find any evidence of damage or abnormal conditions, document it thoroughly with photographs and notes. Next, focus on the facility's grounding system. Use a ground resistance meter to measure the resistance of the grounding electrode system. This measurement should be compared to the requirements specified in the National Electrical Code, NEC, or other applicable standards. Check the size and condition of the grounding conductors to ensure they are adequate for the system's fault current duty. Verify that all grounding connections are tight and free of corrosion. Look for any signs of improper grounding practices, such as using building steel or metallic piping as grounding conductors without proper bonding. If you identify any deficiencies in the grounding system, correct them immediately to ensure personnel safety and equipment protection. Now let's explore the concept of induced current in greater detail. Induced current is caused by electromagnetic fields that are generated by nearby conductors carrying alternating current. When a conductor is placed in an electromagnetic field, a voltage is induced in the conductor, which can cause current to flow. The magnitude of the induced current depends on several factors, including the strength of the electromagnetic field, the length of the conductor, and the distance between the conductor and the source of the field. To minimize induced current, it is important to keep conductors as far away as possible from sources of electromagnetic fields. Shielding can also be used to reduce the amount of electromagnetic radiation that reaches a conductor. In the case of the transformer, the jumper wire could be picking up induced current from nearby high current conductors. Try rerouting the jumper wire to a different location, or shielding it with a metallic conduit to see if this reduces the current flow. It's also important to consider the impact of harmonic currents on the transformer and the grounding system. Harmonic currents are non-sinusoidal currents that can be generated by nonlinear loads such as electronic devices and variable frequency drives. Harmonic currents can cause a variety of problems, including overheating of transformers, increased losses in conductors, and misoperation of protective devices. To mitigate the effects of harmonic currents, it may be necessary to install harmonic filters or to use a transformer that is specifically designed to handle harmonic loads. Here's a list of items to consider when troubleshooting the situation. Firstly, verify the transformer nameplate data, including the voltage and current ratings, impedance, and kVA. Secondly, measure the voltage and current on all three phases of the transformer to ensure that the transformer is operating within its rated parameters. Thirdly, check the transformer oil level and temperature, if applicable. Fourthly, perform an insulation resistance test on the transformer windings to check for insulation breakdown. Fifthly, use a power quality analyzer to monitor the voltage and current waveforms for harmonic distortion. Sixthly, inspect the surge arresters to ensure that they are properly installed and functioning correctly. Seventhly, check the operation of the transformer's protective devices, such as fuses and circuit breakers. Eighthly, verify that the transformer is properly ventilated to prevent overheating. Ninthly, check the tightness of all connections inside the transformer enclosure. Tenthly, inspect the transformer for any signs of oil leaks or other physical damage. Let's discuss the grounding system in more detail. The purpose of the grounding system is to provide a low impedance path for fault currents to return to the source. This helps to ensure that protective devices, such as fuses and circuit breakers, will operate quickly to clear the fault and prevent electrical shock hazards. The grounding system should be designed in accordance with the requirements of the NEC or other applicable standards. The grounding electrode system should consist of one or more grounding electrodes that are bonded together to form a common grounding point. Common types of grounding electrodes include ground rods, ground plates, and underground metallic water pipes. The grounding electrode system should be connected to the equipment grounding conductors, which are used to ground the non-current carrying metal parts of electrical equipment. The equipment grounding conductors should be sized in accordance with the NEC or other applicable standards. In addition to the equipment grounding conductors, a bonding jumper should be used to connect the equipment grounding system to the neutral conductor at the service entrance. This bonding jumper helps to ensure that the neutral conductor and the equipment grounding system are at the same potential, which reduces the risk of electrical shock hazards. Now let's talk about some specific troubleshooting techniques that can be used to identify the source of the high current in the jumper. One technique is to use a clamp on ammeter to measure the current flowing through the jumper at different points along its length. This can help to pinpoint the location where the current is entering the jumper. Another technique is to use a megometer to measure the insulation resistance between the transformer windings and the case. This can help to identify any insulation breakdown that may be causing current to leak into the case. A third technique is to use a thermal camera to scan the transformer case for hot spots. This can help to identify any areas where current is concentrating, which could indicate a ground fault or other problem. If you suspect that the high current is being caused by induced current, try moving the jumper to a different location or shielding it with a metallic conduit. This can help to reduce the amount of electromagnetic radiation that reaches the jumper. Another important consideration is the type of loads that are connected to the transformer. If the transformer is supplying a large number of nonlinear loads, this can cause harmonic currents to flow in the grounding system, which can increase the current in the jumper. In this case, it may be necessary to install harmonic filters to reduce the amount of harmonic distortion. Furthermore, let's consider the NEC requirements for grounding and bonding transformers. NEC Article 450 covers the installation of transformers, including grounding and bonding requirements. Section 450.10 covers guarding transformers, while Section 450.11 covers the ventilation of transformers. Section 250.30 specifically addresses grounding of separately derived systems such as transformers. This section outlines the requirements for establishing a grounding electrode system for the transformer and for bonding the transformer enclosure to the grounding electrode system. Section 250.104 covers bonding of piping systems and exposed structural steel. This section requires that metallic water piping systems and exposed structural steel that are likely to become energized be bonded to the grounding electrode system. It is important to consult the NEC and other applicable standards to ensure that the grounding and bonding system for the transformer is properly installed and maintained. If you are not comfortable performing these troubleshooting steps yourself, it is best to contact a qualified electrician or a transformer manufacturer for assistance. They will have the knowledge and experience to safely and effectively diagnose and repair the problem. Remember, working with electrical equipment can be dangerous, so always take appropriate safety precautions. Wear appropriate personal protective equipment such as gloves and safety glasses. De-energize the equipment before working on it and verify that it is de-energized using a voltage tester. Follow all applicable safety procedures and guidelines. Let's elaborate on the use of a clamp-on ammeter. When using a clamp-on ammeter to measure the current on the jumper, it's essential to ensure that you are only measuring the current flowing through the jumper itself and not any nearby conductors. Isolate the jumper if necessary to get an accurate reading. Take multiple readings at different points along the jumper to identify any variations in current flow. A sudden increase in current at a specific point may indicate a fault or induced current source nearby. Also, consider the limitations of your clamp-on ammeter. Some meters may not be accurate at very low current levels, so choose a meter with appropriate sensitivity for the expected current range. Additionally, some meters may be affected by nearby electromagnetic fields, so take readings in a location that is free from interference. And now, let's discuss the use of a megameter, also known as an insulation resistance tester. A megameter is used to measure the resistance of the insulation between two conductors. In the case of a transformer, it can be used to measure the insulation resistance between the windings and the case, or between the windings themselves. To perform an insulation resistance test, first de-energize the transformer and disconnect it from the power source. Then connect the leads of the megameter to the two conductors that you want to test. Apply a test voltage, typically 500 volts or 1000 volts direct current, and read the resistance value. The insulation resistance should be relatively high, typically several megohms or higher. A low insulation resistance reading indicates that the insulation is degraded and may be allowing current to leak between the conductors. If the insulation resistance is low, the transformer may need to be repaired or replaced. Furthermore, it's crucial to understand the role of bonding in the overall grounding system. Bonding refers to the process of connecting together all metallic parts that are likely to become energized, such as equipment enclosures, conduit, and piping. The purpose of bonding is to create a low impedance path for fault currents to flow back to the source, which helps to ensure that protective devices will operate quickly to clear the fault. Bonding jumpers are used to connect these metallic parts together. The size of the bonding jumpers should be determined in accordance with the NEC or other applicable standards. It is important to ensure that all bonding connections are tight and free of corrosion. Loose or corroded bonding connections can increase the impedance of the fault current path, which can slow down the operation of protective devices and increase the risk of electrical shock hazards. In addition to the points discussed, it is good practice to create a detailed record of all measurements and observations made during the troubleshooting process. This record can be helpful for identifying trends over time and for comparing results with previous measurements. The record should include the date and time of the measurements, the equipment used, the test conditions, and the results obtained. It should also include any notes or observations that were made during the troubleshooting process. This record can be a valuable tool for future troubleshooting efforts. Remember, a systematic and thorough approach is key to successfully troubleshooting electrical problems. By following the steps outlined and carefully considering all possible causes, one can effectively identify and resolve the issue of high current on the transformer jumper. And as always, safety should be the top priority.